So for doing this problem here, we're still going to be using the same formula that we've been using the last couple of days. Now, you remember what formula that is, right?
Yes. A equals T.
And so you hopefully are thinking of this formula. Now, you already got it in your notes, so it's not like you got to write it down again. But I want to remind you that this is what we're using. Now, the reason why I know that I'm going back to this formula is because this is about compounding interest. And compounding interest happens when we're dealing with something that increases or decreases by a percent. And so since it's increasing by that 0.25%, I know that this is the formula I'm using. All right, so let's go ahead and start plugging in the information that we know in this problem. First of all, A of t. A is our final amount, so that's actually what I'm trying to figure out here. So I'm going to leave that as A. So it's A of t. Do we know what t is here?
Time.
It is time. Do we know what the time is? What number it is?
8.
It is 8, yes. So we're going to do A of 8 equals P. What is P?
500.
Yep, P is 500. That is principal. That's technically what it stands for because principal means the starting amount when we're dealing with financial stuff. And then 1 plus R. Now this, if anything, is going to throw you off in this problem. It is probably the R value. Because R here is not 0.25. It's 0.25%, which I have to then turn into a decimal, which we do by dividing it by 100. And so R is actually going to be, if we do 0.25 divided by 100, you get 0.0025. So 1 plus 0.0025 to the power of t. And t, remember we already talked about t back here. T was 8. So that's going to be to the power of 8. So now we have our equation. Now it's just a matter of calculating out what is that value. So on your calculator, go ahead and do that calculation. Right, when all is said and done, you should be getting an answer here of $510.09. That's not exactly a lot more than what we started with, is it? In terms of real-world application here of what we're looking at, this is talking about a savings account. Now, a savings account these days, if you're getting even 0.25%, you're doing pretty well in a savings account these days. Rates are very, very low for such things. And so you can see that even after 8 years, you only made $10 in that thing. This would not be really a wise investment. If you're trying to put your money someplace where it's going to grow, a savings account is not the place. A savings account is just a place to keep your money safe in case you need it. It's not an investment. Those are different ideas. Now, what if we had an account that decreased in value? Well, first of all, get a new bank. But if our account decreased in value by 0.25% each year, what would change in our equation? We got the original equation here already. And there's one little change we need to make. Yeah, when we were increasing, that meant that our rate was positive. If we're decreasing, our rate is negative. So plus a negative 0.0025 means we're actually doing 1 minus 0.0025. And so basically when you are decreasing in value, really what it means is that you're now subtracting instead of adding. And so that gives me something that looks like this, which I can go ahead and calculate that out. So it gives us $490.09 if it went down by that same amount.
Lost $10.91.
Now, on this one, something I want to point out between these two, something that can help in just kind of processing these through. You notice in the first one, I gained 0.0025 each year. I gained 0.25%. So notice that was 1 plus the 0.0025. It basically is saying that each year I have 1.0025 times as much as what I started with. The same kind of thing can happen down here. Except to put it a different way, that 0.9975, that's like 99.75%.
Wait, how'd you get that?
Because if I want to turn the decimal into a percent, I multiply it by 100. Not that you would do that in this problem, but I want to illustrate to you that what that means is that each year if it's decreasing by that 0.25%, each year I'm left with 99.75% of what I started with. And so that decimal that's in there with the 1 plus or the 1 minus is really a descriptor of what percent of my original amount will I have next year. Kind of just going back and reminding us why this formula works the way it does. Right, we're also going to be taking a look at this problem and a variation of it. So in this case, when we turn 18, your aunt gives you $1,000 in a retirement account. That is a very nice aunt, right? Which, by the way, is probably a really cool thing where if you find yourself able to do so, that's a neat thing to be able to do for any of your nieces, nephews, or other people in your family that you want to try to help out. Get them started in a retirement account. But back to our problem here. Now, if that $1,000 investment averages 11% a year, so we're talking about an investment averaging 11%, so we're assuming that it's increasing by 11%. How much money will we have if we want to retire at age 60? So in other words, how much will this be worth by the time we turn 60? Now, are we going to use that same A of t equation for this one?
Yeah. No.
Yes. Because I'm going up by a percent. Anytime we're increasing or decreasing by a percent, I know to use that equation. All right, so with that in mind, I can already know a lot of the pieces here, but the one that I think is going to be a little bit tricky is the 42. Why did I plug in 42?
Oh, I know.
We got this investment when we were 18 years old, and I want to know what's it going to be like when I'm 60, so we did 60 minus 18, yeah, which gave us 42. And so what we need to do is remember that since this is the amount of time that it's sitting in there, that doesn't represent how old are we, it's how long did it sit in there and grow. And so that's why we plug in the 42. Once we've done that, of course, then it's the same thing we've been doing. Do the addition first, then raise it to the power of 42 and multiply it by 1,000. And so this kind aunt who gave us just $1,000 actually got us $80,000.
That's a nice ass aunt.
That ends up being a really nice gift. One little side note here. If your aunt gives you the $1,000 gift in the retirement account and the very first thing you do is pull it out so you can go spend it on a game system, you will barely be able to afford the game system and you won't have $80,000 when you turn 60. And I say that you'll barely be able to afford the game system only because if you pull money out of retirement accounts early, they penalize you like crazy for doing so. And you get taxed on it, and yeah, that $1,000 very quickly becomes somewhere between $300 and $500. So once it's in a retirement account, you leave it there until you're ready to retire. If there is any lesson you could get out of this class, that would be the most useful one, even besides all the math. Now, this, of course, is a very kind aunt, and really based on the rules and regulations about retirement accounts, this is probably about as early as a person could give you a gift that goes into a retirement account. But let's play around with this a little bit. What if we were able to give such a gift when the person was born instead? So
you change the 42 to 60.
We get $1,000 when we're born. We still want to retire when we're 60 years old. What is that going to do? All right, so in this case then, since we're given it when we're born, we still are looking to retire when we're 60. Then that means that in for t, we're actually plugging in the 60. The full 60 years. And when we do that calculation then,
I knew it.
we get 524,000. So notice what just 18 years more did. Just 18 more years took us from 80,000 to over 500,000.